All right, so we're going to continue on with our discussion of charge. In this tutorial, we're going to quantify charge. We're going to introduce a new unit you're not familiar with, and then we're going to learn how to convert back and forth between a total amount of charge and the individual carriers of those charge. It's similar to looking at eggs. You can eat one egg at a time, but normally you buy eggs by the dozen. Okay, so we're going to come up with something like that and go away from the way you quantify charge or charged ions in chemistry. So that's going to be the, if you will, difficult part. All right, to start off, we know that charge is carried by objects, and the fundamental carrier of charge is either the electron or the proton. Okay, now there are other charge-carrying particles that exist in nature, but we're going to stick with what's part of the atom. You also know the neutron carries no charge, so that's not going to play any role in our discussion today. And we learned last year in chemistry that if the electron carried a charge of -1 and a proton carried a charge of +1. But in physics, those numbers really have no meaning other than you're talking about one extra electron or 1 or 5 excess electrons. We want to quantify in terms of a value that fits in with the forces that arise because of it and any other phenomenon that are dependent on charge. Okay, so for example, when we did the tape demonstrations, or if I rub my hair with rub a balloon against my hair, it will take on charge. Or when I charged up the static generator, a lot of charge was built up, or I should say a lot of electrons were building up and up and up. So we need something more than just saying an extra 5,600,000 electrons was transferred. That leads us to the idea of a metric unit of charge. It is called the Coulomb, named after Charles Coulomb, a very important French physicist that did work around the time of Benjamin Franklin. So the symbol for charge, I should make that clear, is lowercase q or sometimes uppercase q, and we measure it in coulombs. Okay, so I might say, oh, I've got q is equal to 0.5 coulombs. All right, that's just telling you how much charge we have. It's kind of like saying my mass is 0.5 kilograms. Now, what we want to be careful of is that 1 coulomb of charge does not equal the charge of 1 electron. 1 electron is a teeny amount of coulombs, because a coulomb is an aggregate. It is a package of electrons, and we'll establish that number in a few minutes. But it's kind of like saying 1 dozen is equal to 1 egg. We know that's not true. So a dozen is a package like a coulomb, and it's made up of fundamental units called eggs. All right. So in fact, 1 coulomb charge is about as much as a lightning bolt. That's a lot of charge. So it tells you 1 coulomb is a huge quantity of charge, unlike 1 kilogram, which is a moderate to small amount of mass, or 1 meter is a moderate to a small amount of distance. Okay, so just basically, well, I won't go into the details of why a coulomb or 1 coulomb is such a large value, or why they would make it like that, but it has to be consistent with everything else that we can measure. So when we got shocked, or as a class, by the static generator, you might be wondering, well, how much charge was transferred? Well, it definitely wasn't a lightning bolt, so it was definitely less than 1 coulomb. It was around 1 microcoulomb. Okay, and that, of course, is 1 times 10 to the -6 coulombs. So every day getting a decent shock, you're talking a millionth of a coulomb. All right, so you can feel it. It's annoying, but it's not going to harm you. Millicoulombs, dangerous potentially. Coulombs definitely will kill you. All right, so the next number we want is probably the most important number over the next week or so. Okay, and that is how much charge does an elementary charge carry? An elementary charge is essentially an electron or a proton. In other words, it's the smallest possible charge we can get. It's like 1 egg in a dozen. So we want to know how many coulombs is 1 charge. And this is what took us a long time to figure out experimentally. It's one of the more famous experiments, but it's not something we're going to talk about until after the AP. Anyway, long story short, 1 elementary charge is 1.6 times 10 to the -19th coulombs. This is a very, very important number. It is in your reference table, so it's not something you have to memorize, but we want to be able to apply it in a lot of different situations. So again, 1e equals 1.6 times 10 to the -19th coulombs. We're going to convert that back and forth. Now that 1e certainly it could mean electron, but it could also mean a proton. So don't forget that. All right, and then we could ask the question, well then, if a Coulomb is a package of elementary charges, how many elementary charges does it take to make 1 Coulomb? And that's really just the inverse of this number. So if I take the reciprocal of that, I will get another conversion factor, 6.25 times 10 to the 18th elementary charges are in a Coulomb. Okay, so either one can be used, but generally it's the first one, the 1.6 times 10 to the negative 19th, that is used in equations. All right, so let's do a few examples to finish up here. All right, so about how many charges are transferred from the Earth to the static generator when we charge it up? So remember, the static generator starts off neutral, and when it becomes charged, we're adding excess of negatives on there. Now, you didn't know there was negative charge. I'm telling you right now. And we already just learned that the Q of the static generator is about 1 times 10 to the negative 6 coulombs. Sorry, that should be a 6, not a 16. So how do we convert that to the number of extra charges? Well, we just use the conversion factor. And I'm going to do this with a little what's the word I want? 2-square table, because I've used this before and it helps kids know how to set things up. It's very much like you did in chemistry when you had line units. So I want to convert coulombs to elementary charges. These are E's. So I'm going to take what I start, the given, 1.6 times 10 to the negative, I'm sorry, wrong number, 1 times 10 to the negative 6 coulombs. So that's my given value. I always put that in the upper left. And I'm going to put the units, and I automatically put it over 1. I'm really just doing it proportions. Now I'm going to take my conversion factor. My conversion factor that I like to use for all these problems, just for consistency's sake, is this one right here. So that says 1E equals this. Now I just got to put the 1E in on one part here and then the coulombs in the other. Since I want E's, I'm going to put the 1E up here from this, and then I'm going to put what it's equivalent to on the denominator. Okay, coulombs. So I can see that the coulombs are going to cancel out, and it tells me I just take this number and divide it by this number, and that will give me 6.25 times 10 to the, I believe, well, I could be wrong about that. Negative 6 times 10, negative 19 is negative 13. I believe negative 12 coulombs. Excuse me. My bad, I'm way up. Times positive 12 electrons. I forget what I was going to do. So we're talking about 6 trillion electrons in excess of normal are on that charge generator. All right? And then we can reverse the problem. I can say, let's say I have a tiny oil drop, all right, that has a deficit, that's important for later, of about 2,300 electrons. So we've stripped 2,300 electrons from that oil drop. We want to know what's its charge in coulombs. So once again, I'm going to make this 4-square table. I'm going to take my given piece of information, 2.3 times 10 to the 3, and I'm going to put the units, electrons, or just E's. Always put it over 1. Now I want to use my conversion factor, which is right here. I want the coulombs as my final answer, so now I'm going to put it on top, 1.6 times 10 to the negative 19th, and coulombs all over per E. Now I can see I simply multiply these. Okay, so if I get out the old handy calculator, 2.3 times 1.6, I see I get about 3.7 times 10 to the negative 16th coulombs. Okay, so it's still a tiny amount of charge, but it's bigger than 1 electron. In fact, it's 2,300 times this. So that should be pretty straightforward. All right, I consider this next one a pretty interesting problem, but it's very similar to what we're doing. What is the charge of all the electrons in 1 mole of helium if we know that there are 2 electrons per atom and that there are Avogadro's number of atoms in a mole? Okay, so this is very similar to a problem you guys did last year. So I'm just going to walk you through it in terms of lining up all the units. All right, so I'm going to start what I know about the helium atom. I know that I have 2 electrons per atom, right? And I know that there are 6.02 times 10 to the 23, atoms per mole. Okay. What else do I know? I have 1 mole And then the last thing I know is I want to know how much charge, Q, so I know that there is 1.6 times 10 to the negative 19 coulombs per electron. Okay, there's that very important conversion factor. And if I look at my units, electrons cancel out, moles cancel out, atoms cancel out, and I left with 2 times 6.02 times 1.6 times 10 to the negative 19. You multiply that, and you get about 192,000 coulombs. And that's a lot of charge. That's about 200,000 lightning bolts worth of charge in 1 mole of helium gas, which would be about 22 liters, like a little box. So it tells you there's a tremendous amount of charge in nature, but we don't get destroyed by it because there's equal amounts of positives to keep everything more or less neutral. So the trick is to try to strip those electrons off something to get to that, but that requires energy. All right, last problem. Could this charge be found in nature? Well, let's think about how we build up charge. The smallest charge we can get is this. And that's 1. If I have 2 of them, then I've got 3.2 times 10 to the negative 19th coulombs. So there's no value of charge between those 2 numbers. So if I got this charge and I want to know, can it exist, it has to be a multiple of that value. So what I can do is I can take 3.4 times 10 to the negative 18th divided by 1.6 times 10 to the negative 19th. And if I get a whole number, then I'm good. If I don't, then it can't exist. So this comes out to be 21.25. You can't have a fraction of an elementary charge, so that charge is not allowed. If I take 21 times this, then that value is allowed. So we'll do a little bit more with that later. Okay, so that concludes our introduction to measurements of charge. Now we'll use it to calculate forces in the next lesson.